So, good morning. So, let me thank the organizer for inviting me to come to this very exciting symposium. My name is Anugrah Singh. I'm from IIT Guwahati, and I'll be presenting work which was done by my students, Nasaba, Konidena, Sadav, and Mallikarjun Reddy. So, those of you who don't know where I'm at, so I am from Guwahati, which is in northeast of India. You can see right now we are somewhere here. So, it's a different geography. So, you have different flora and fauna. So, this is the picture of our campus. This is a real back view from our guest house, and this is the academic complex right on the bank of mighty river Brahmaputra. It's the male river in India. Most of the rivers are female, and this is male river. And Assam is also famous for rhinoceros, one-horned rhino. And nearby, you also have a place called Meghalaya. It's called Abode of Clouds. Yesterday, we had a talk by Rama about clouds. Here, you have so much of clouds and rain. It was famous for most wettest place on earth a few years back. So you can see the clouds not above. You can see, at ground level. So my talk will be on particle migration in rotating suspension. These are not active suspension, but they do find a lot of applications when we deal about reactors, especially biological reactors. So first I'll talk about introduction, and then some experiment which we have done with rotating suspension. And then we try to understand using point particle simulation as well as continuum simulation. And we try to see that if the particle migration and secondary flow can explain the radial and axial patterns. And then if time permits, I'll also tell you that how do we control migration in rotating flow and some practical applications. So coming back to introduction, the rotating suspension, especially in cylinder, has received a lot of attention because of the practical application in concrete mixtures. You have pan coater, tablet coater. So their idea is to coat the solid particles with viscous fluid. And in mixture, you want to mix it. So in these applications, mostly the particles are heavier, they are sedimenting. You also have a lot of applications where the particles may be floating, less denser than the fluid, or you could have a mixture of particles. Some are floating, some are sedimenting. So though these rotating suspension last decade had received wide attention, but the interest of fluid mechanics community decreased, probably thinking that this migration and pattern formation is resolved. But then this has been kept active by biological community, especially in rotating bioreactor, where you can keep these particles suspended just by rotating at low rotation, because you want to avoid shear and you want to avoid turbulence. Otherwise, they will sort of damage the cells. So you have various kind of rotating bioreactor. Okay. Now, coming to this, the problem of segregation in rotating suspension. So you can see if you have a suspension of settling particle in a cylinder, if you rotate at very high speed, you can see the bands of particle intervened by the clear fluid. This was, by Bute Thomas, later by Gues Thomas. It was also observed at low Reynolds number, where you have particle Reynolds number very small. Then also, if you have the partially filled cylinder, then you also have this axial band formation observed by Thirim-Kudlow et al. In either drum flow or in cylindrical cuvette flow. So it was proposed that you need to have a free surface. For low Reynolds number, you need to have a free surface, which basically develops instability, and these patterns are formed. But later, Madsen et al., they also observed that even if you have completely filled cylinder, but instead of the particle neutrally buoyant, if you have settling particles, particles heavier than the fluid, okay, then also you do see these patterns forming. Okay. So later, Lee and Lard carried out Stokesian simulation, considering these particles as point particle. And by looking at the motion of this particle, in this case, the blue ones are moving towards one direction and the red ones towards the other, they could infer that there is cluster formation and axial segregation. And they could also see in the concentration plot that you do get the peaks, and the wavelength of these peaks are of the order of what you observed in the experiment, which is of the order of the diameter of the cylinder. They also propose that these segregation in settling suspension occurs because of you have differential centrifugation, because of the relative position of these sedimenting particle. It will drive these particles to come closer. So you have attractive interaction in the centrifuge in the sedimenting particle, and that's what you see this particle forming cluster. So they also predicted that in positively buoyant particle, floating particle, you will not have this kind of, they will basically homogeneously mixed and you may not get segregation. However, Kalenka et al. Performed experiment with buoyant particle as well, and here is the comparison of buoyant and settling one. You can differentiate the whole regime into broadly two regimes, one when you have gravity dominated, another when you have centrifugal force dominated. So if you see the forces on the particle, you have three forces. You have viscous drag forces, gravity, buoyancy corrected gravity, and you have centrifugal forces. Balance of these forces basically decides you what regime you will have. So these are at different rotation speed. So in this case, the gravity dominates. So you can see that the particles are not homogeneously dispersed, not filling the full cylinder. But at little higher rotation, when the particles are able to leave the beds, you can see the formation of these bands for both buoyant as well as settling. Right? And this is in the radial plane. The radial plane also in the gravity dominated regime, the patterns can be correlated. So you can think that settling is opposite of buoyancy. But however, in centrifugal dominated regime, you can see the both axial and the radial patterns are different. Okay? In these pictures, you can see that the buoyant particles still form the axial band, whereas the sedimenting particle or settling particles, the bands disperse. Okay? And eventually what will happen that the settling particle will go to the, because of centrifugal action, will go to the wall, whereas the buoyant particle will form a core in the center. Okay. So this has motivated us to look us again into the floating particle suspension, and also what happens when you have mixture of these particles. So these are the questions we try to answer. What is the behavior when I have a mixture of floating and settling particle? What if I have non-spherical particle instead of a spherical particle? So these two I try to address by doing experiment. And then the question that if we can explain it through the point particle simulation. So what is the radial and axial segregation of floating suspension? And when does the transition occurs between different phases? So these we have addressed through the Stokesian simulation of point particle approach. And to understand that what causes the onset of segregation. This is something which was debated. Earlier it was thought that diffusion of the particle coupled with the instability at the free surface, and then the viscosity which varies with the particle fraction, these basically can cause you the banding. Okay. However, there were studies where they had basically predicted or they had calculated that the shear-reduced particle migration rate is too weak, whereas you do see these action happening at much faster rate. So shear-induced migration cannot be thought of a reason for onset of these patterns. So we have looked again into the role of particle migration and secondary flow in rotating suspension. So experiment we did two types. One in the axial case where you have long cylinder so that you can see the axial bands developing. To study the radial flow, the similar setup, except that the length of the cylinder was much shorter, so we wanted to suppress the any axial segregation. And in this case, the camera was just looking at in the radial plane, whereas in this case, we are looking at the side. These are the one when I have monodispersed settling particles. So you see that at low rotation, all the particles are mostly in the form of a bed. I call it the granular bed. Okay. As you increase the rotation, you can see small, at local points, these particles, some of the particles, they try to rise up, and the regime is called fingering regime, right? In the form of various fingers, they try to rise up. These fingers become more prominent at little higher rotation, and at much higher rotations, these fingers, they join and they try to form the band. This is called low rotation transition regime. And these are not very stable. The bands get enriched, okay, and then finally at certain RPM, at higher RPM, what you get is the stable band, which you'll not see much movement. It will be stable for some time, and then after that, the centrifugal force will overtake, and you will see that there will be again change in the number of bands and their positions. If you see the floating particle, now particles are lighter. These are the properties, okay? So in this case, the density difference was higher, 1.3. In this case, the density difference was much smaller, right? So one can think that if you do not see any pattern formation for neutrally buoyant, when you have same density of particle and fluid, okay? So you should also see suppressed segregation when you have small density difference. That is reverse, right? You see in this case of floating suspension, band formation occurs much earlier compared to settling one where you have large density difference, okay? The reason here is that because of the very small density difference, the particle in floating bed are very easily able to come out. So in order to form this band, the particle needs to come out of the bed. As long as they are in the bed, you don't see the band formation, right? And that's the reason why for floating suspension, the banding occurs at much lower rotation rate. So you also see homogeneous regions where the particles are homogeneously dispersed at higher RPM, and then after homogeneous region, you can see stable band formation, followed by this stable band again break. So you can see that the particles from the band, they are losing to the other bands. So you can see some are smearing, some are concentrating. And then we see also the discrete banding where they are not uniform, they are now discrete. Next, we mix these particles. So we have few particles, 50% of the particles were settling and 50% of the particle were buoyant. So this is what initial bed of floating one and the sedimenting one. And you can see these are the two views. One is looking at the rising side of the cylinder. So you can see the bed of these settling particle. Another is falling side. So you can see the floating particle. So what we see that the floating particle, they try to form bands. So you can see the fingers, right? But as you increase the speed, the settling particle also try to raise up. They also try to form fingers, right? And settling particles, they are more massive, they win actually, and their fingers destroys the finger what the floating particle are trying to form. As a result, you do not see the fingers or the bands by floating particle even at much higher RPM, right? Previous case, even at 10 RPM, I could see the formation. Even now, you do not see up to 46.3 RPM also. It's because the settling particles, they are disturbing the band formation of the heavier lighter particle. Right? They are not allowing them to form. And in turn, is the settling particle which forms the band. Right? They do not give much room, so floating particles are homogeneously distributed. Only when the RPM, you have enough RPM, so that the settling particle goes to the periphery of the cylinder, you have enough room for the floating particle to form band, but they are also not very clear as much you have for the settling particle. So the gist is that if you mix settling particle to a suspension of floating particle, the floating particle will be more homogeneously dispersed in the system. If you have cylindrical particle, these are the case for monodisperse. We had particles in the form of short cylinders, aspect ratio nearly 3. So 3 millimeter long and about a millimeter diameter. What we see is little different behavior than what it was for the spherical settling particle. You can see that the fingers are in the form of small webs. They are not very prominent finger. It's because the cylindrical particle they find difficult. There will be more drag on the cylindrical particle. So they are not able to easily go leave the bed. Instead, what you see that you will see undulations at higher RPM, and then you will have the cluster of these cylindrical particles coming together. And these clusters, they get enriched, till some point. After certain RPM, you see this, the particles in this cluster, they start losing, and you'll see the depletion of this band. And finally, at centrifugal limit, you can see that some of the bands, they lose particles, and some of the others get enriched. Right? So if you look at the closer view, what we interestingly observed that the bands in this case were much more stable. We observed that there are clusters being formed, and these are basically not allowing particles, the other particles to leave through. Even if one wants to leave through, it encounters a lot of drag. So the bands here are much more stable. Finally, when the centrifugal force takes over, you can see the particles leaving. And when they leave, the orientation of these particles are along the wall. Whereas in all these cases, when you have cluster formation, they are more random oriented. So what we understood from cylindrical particle is that when you have these non-isometric particles, the bands are more stable. Okay? And so for longer period, you can see the stable band formation compared to what you have for the spherical particle. This is the case when I had floating spherical particle and the settling particle was cylindrical in shape. In this case, we observed that like what you had for the spherical settling particle, again you see the settling particle disturbs the band formation. So bands, all you see for the settling particle, cylindrical particle, the floating particle which were uncolored, they are all dispersed dispersed throughout this cylinder. It's only, if you look at the closer view, it's only at much higher RPM, okay, you see that this there is enough room for the floating particle to form the band. And when they do form the band, they form in the core. So all the cylindrical particles are thrown because of centrifugal forces to the wall of the cylinder, and the floating particle, they occupy the core region. But the position of these bands are exactly at the same location. We also looked at the phase profile. So we had colored the cylindrical particle and the spherical particle were not colored. These are the pseudography image. And we also did PIV measurement to look at how the velocity profile of these floating particles look like. So what interestingly we observed that the bed of the cylindrical particle, they try to rise up along the wall of the cylinder. However, at little higher RPM, when they try to rise up, the cylindrical particle try to rotate. So some of the particles leave. Not all particles leave the bed, some of them leave. And when they leave, they are basically because of the rotating cylinder, they are carried away. As a result, at higher RPM, you can see there are multiple bands, multiple rings formed. These are all in radial plane, right? This was not observed when you have spherical particle, both spherical as floating as well as sedimenting. So you can see this multiple rings of formed by the cylindrical particle persist for some RPM. And these floating particles, they get sucked into the space left by the cylindrical particle and they come to the core. As a result, you can see that the most of the floating particles are rotating on this side. As you increase the RPM, they try to come to the center and finally they become more symmetric, okay, and the cylindrical particle occupy mostly the region which is close to the wall of the cylinder. Yeah, so finally centrifugal force dominated, all the floating particle, they come to the center and the cylindrical particle, they go to the wall of the cylinder. As you can see that the behavior is quite different when I had, instead of cylindrical particle, I had bed of the spherical particle which were settling. You do not see multiple rings. Instead, what we see is that these particles, they try to rise up, but then they also fall down. Okay? And it's not very clear. When they try to fall down, they form this finger like a pattern, right? So you have floating particle and then you have settling particle, they are trying to protrude in a finger kind of. This was manifested as a finger in your radial pattern. Right? So at higher RPM, these particles go, the settling particle goes to the wall of the cylinder and the floating one comes to the center, right, as expected. So what we understood is that if we mix heavier particle in a suspension of lighter particle, it is going to aid into suspension or homogenization of the floating particle. We also looked at through the point particle simulation. So if you have many particles in a cylinder and if you consider as to be point particle, you can relate the velocity of any particle to the hydrodynamic force on itself or the drag force, and then these are the non-self term because of the interaction with all other particles. right? So this G is basically the green function for the particular geometry, in this case the cylindrical geometry. So the green function for the rotating cylinder geometry can be written as the green function in unbounded system plus the wall correction. So for a single Stokes-Slate, single point K particle in a rotating cylinder, Lear and Sahar has given the expression for the green function, and Lee and Ladd basically extended their method for n Stokes-Slate in a cylinder. Right? So this is the green function for unbounded system. The wall corrections basically it involves Fourier transformation, and this can be found out in the paper by Lee and Ladd. So we have used the method of Lee and Ladd. Instead of studying the sedimenting system, what they have studied, we have tried to understand what if I have a floating system. So though these are the point particles, we give them some finite radius, finite size. Why? Because one thing is that you need to decide the time scale. So if you can solve the velocity field, you integrate with time, you can find out how the microstructure is being evolved, right? So in order to set the time scale for the integration, you have to give them radius, and the time scale has to be much smaller than the time scale for this particle to avoid collision. So we call it Stokes time scale. So you can find out Stokes time scale by using some characteristic velocity scale. In this case, it was used as the settling velocity was used as the characteristic velocity scale. So we have taken the time steps much smaller than the Stokes time. We used 100 micron particle, and radius of cylinder was 100 times. And this was infinite cylinder in axial direction, so periodic boundary conditions were used. Okay. For radial studies, it was short cylinder, and for axial studies, it was long cylinder. Right. So these are some results for monodispersed case. Now these are not bidispersed. What we have done is we have color coding. So red means the particles have a sort of direction downward, and the blue means they are trying to go up. So as you can see, at rotation increases, the bed of the particle, it gets dragged along the wall, but at a certain point, the viscous drag, and gravity is such a way that the buoyancy takes over, and then again the particles try to rise. While in the process the particles are rising, it will dislodge some more particles from the top bed, and it will set up the circulation in this region. At higher rotation, this circulation widens up, and you can see that now it has mostly covered almost the whole cylinder. So these were at low rotation. We also did at gravity centrifugal force dominated regime. So you can see the homogeneous distribution, and then when the centrifugal force takes over, you can see the particles spiraling and going to the form the core, which was also observed in the experiment. These are the distribution of the particle, initial distribution at certain rotation. So at low rotation, you see only after few rotation, 1.2 rotation, almost steady state was reached. I mean, they were not changing much. Whereas if you go for fingering flow and low rotation transition, you need to take more revolution in order to get the steady distribution. What interesting we observe is that in centrifugal force dominated regime, finally when the centrifugal force takes over and the particles go to the center, they form the core is not very symmetric. You can see it's asymmetry. It's because the particles which initially started from homogeneous distribution do not reach the at the same time. So because of the random perturbation in the radial distribution, you also see the finally you have basically asymmetry. And it has some resemblance to what in experiment Kozlov has obtained, when instead of considering two particles, they have considered two immiscible liquid. One was lighter, another was heavier. So heavier fluid was in case it was buoyant, but then the one which has more density difference coming to the center, and the core was also not very symmetric. It was very similar to what we observed. We can also find out an order parameter. So you can find out the average rotation angular speed of all the particle and scale with the rotation rate of the cylinder. That's the order parameter. So what we observe is that it's not the particle size. These are for different number density of particle. So it's not the particle size, but it's the interparticle distance, which is basically the characteristic length of the, in this case of the order parameter. This is the actual case. So this was initial distribution of the particle. After you set the motion, and when you see after many rotations. So these are for low RPM homogeneous regime. These are for local structure dropout, and these are for centrifugal. You can see the core formation. So you can clearly see that you have the band formation because you see group of the particle which are either moving left or moving right. What we observe that if you look at a different time, that these bands what they form, they are not stable. They keep on moving. So these what we call traveling band. They were also observed in the experiment for certain RPM. So we do see traveling band, for some cases. When we slightly change the density, in this case the particle density was 0.15, fluid was 1.16. When we slightly change the density, what we see that the traveling band disappeared, and what we observe is the stable band. Now these bands are stable, do not move with time. Right? So this was also observed in the experiment that for certain condition you do see stable band. So density difference plays an important role in deciding the phases, whether you have stable band or whether you have traveling bands. Yeah. So these are some studies, in the radial plane. But not with monodisperse. These are with bi-density settling case. So you have the particle, both are heavier than the fluid. One is more heavier, another is comparatively lighter. Now we see what happens in two regimes. One is gravity dominated regime, and another you have centrifugal force dominated regime. As you can see, this is called sedimenting system, where you have the heavier particle and the lighter particle on the top. And as you rotate it little higher RPM, you can see that there is a core formation. The heavier particles are in the core, and the lighter ones around us, the heavier one. And at more RPM, as you increase, you can see that the lighter one, they disperse more easily. The heavier one are still forming the bed. Some of them, they do leave the bed, but they are still close to the rising side of the cylinder. Eventually, they also rise up. However, they do see a lot of interaction between them, which you can clearly see in this picture. This is where the forces exactly balance. So you can see homogeneous region. Both heavy and light particles are homogeneously dispersed. What you would have expected that if I increase rotation rate, in this case more and more both heavier particle and lighter particle should be moving towards the wall. The heavier one does. So finally it does concentrate towards the wall, where the lighter one does not. Right. So what is happening here is the heavier particles, they are making the lighter particle disperse. Right. This is very clear. Even if all the heavier particles have gone to the wall because of centrifugal forces, the lighter particle was still not in centrifugal force dominated regime. Right. So now there is no interference by the heavier particle on the lighter particle. So it still comes back to the bed. Only at much higher RPM, when the centrifugal force dominate, eventually the lighter ones as well as the heavier one, they form the bed. So in this regime, we can take advantage of dispersing the heavier particle to make homogeneous dispersion. That is one of the objective of this study, that how to make the floating or one kind of suspension distributed by the other. Similar thing we also noticed, instead of sedimenting, we had floating, and we studied what we have. One is less denser, another is more denser. So we also observed similar one, except that in the centrifugal force dominated regime, the phases were not correlated. Nonetheless, in this case also we can see that even if it is not driven completely by centrifugal force, you can see that in certain speed regime, we can disperse the lighter particle by the heavier ones. We also looked at structure transition map. So I will mention what this means. This FT means fingering phase, floating phase. CF means co-formation. S1 is segregation 1. PM is partially mixed case. M is completely mixed case. Again, after completely mixed, it becomes partially mixed, and then these are basically segregation phase 2, and these are centrifugal limit case. So at what density ratio these and what speed these transition occurs, so it can be studied by structural transition map. We have the triangle one source for the sedimenting particle system and the circle source for the buoyant system. So we have basically used power law fit to see what is the scaling with the ratio of density of heavier particle to that of the lighter particle. And you can see for the gravity dominated regime, okay, since the phases were observed at different rotation rate for centrifugal sedimenting and floating particle, nonetheless they all fall in the linear feet. This says that gravity dominated regime for floating as well as settling system are identical. They are correlated as expected because it's the direction changes. However, in the centrifugal force dominated regime, they are not. Even though they are linear, they are just opposite, right? So this one for the sedimenting case is going down and this is going up. It's because of the direction of centrifugal force. 10 minutes? 9 minutes. Okay, yeah, I can wind it up. It's because direction changes. For settling system, the centrifugal force will take the particles to the wall. In the floating system, it will bring to the core formation. So this was also okay. We proves what Kalenker has observed. Now the question comes, what initiated the actual segregation? This is important, right? If you see the initial distribution and you see the final one, right? Initial distribution in our study as well as the study of Lee and Ladd, they had some kind of axial perturbation, which is also clear from if you see the number density plot against the axis. So if we start with completely homogeneous, it didn't give us the stable band formation within the time scale. These are quite time consuming simulation, but when we have some perturbation, axial perturbation, it eventually evolves into the band formation. But what actually initiates, okay, what causes the onset of segregation has been debated. Okay. Like Timberlake and Morris, they did some scaling analysis and discarded that shear induced migration cannot play a role because time scales are very different. Okay. But nonetheless, we try to look back again. Why? Because in Timberlake Morris, their analysis was not considering wall effect into picture, wherein in real all experimental system, you do have the walls. And it's near the wall where the first band appears, right? So the wall appears to change not only the shear rate profile, they also are the one where the onset starts. So we consider the simulation in bounded case, right? So I'll skip the models. So basically you have two continuum models for particle migration. So where we consider the whole suspension as phase, so you solve continuity and momentum equation. And in addition, you also solve the convection diffusion equation for the particle phase. So you have this diffusion, the flux, okay, which can be of various reasons. Could be Brownian diffusion, could be because of sedimentation or shear rate gradient or viscosity gradient. So you have two model, diffusive flux model and you have suspension balance model. So a diffusive flux model is very simple, okay. So you solve continuity and momentum, you solve particle transport equation. So the flux could be decomposed into one due to variation in viscosity of suspension, another is because of the frequency, right? And these are the phenomenological parameter you can obtain from the experiment. Another is suspension balance model by Knott and Brady. So it is little different because it considered another phase is called particle phase. So you have equation for the whole suspension and you also for the particle phase. So the particle phase equations gives you the flux expression for the flux of the particle, which is basically gives you the divergence of the stresses, right? So these are the particle stresses, and these particle stresses are non-isotropic, and which is the one is responsible for secondary flow. So Morris and Bowley have basically formulated the expression to tackle the particle stresses. So you have normal part and they have shear stress part. So normal stress part is model which in the similar fashion, but you have the scaling which depends on the particle concentration and the shear rate. And since these particle stresses are anisotropic, so you have to multiply by anisotropic parametric tensor. So these are the value k which works well for the monodispersed suspension, 0.8 and 0.5. So these are basically not normal stress differences. These are the ratio of 22 to 11 and 33 to 11. Okay. So we used it for settling suspension, but you need little modification. You also need to add the term which is basically body force term arising due to the density difference between the fluid and particle. 5 minutes? Okay. Yeah. Okay, I'll try to wind it up. So we did K and you use the mixture viscosity, and we use the same parameter as was in the experiments of Matson et al. Except that they use 2% particle concentration, we use 10%, because the concentration of particle only increases the speed of the formation. It doesn't change much qualitatively. There was no initial distribution, there was no axial distribution, but there was radial gradient, which you also see when you have settling suspension or floating. You do see the density gradient. What we observe is that after certain rotation, you can see the appearance of this band, right? These are in the radial plane, okay, I'll skip. And finally, okay, after certain rotation, the center of these vortices are off-centered because you have the rising, particle rising along this side. And these are the experiments. So the positions were exactly same what we observed in the experiment, right? So you can see that the particle concentration near the wall is much higher, okay? So it's near the wall which, you see the first band appears. That was also observed in the experiment. And finally, these bands are more stable. They were not regular because we did not continue simulation for long. But you do see the bands which are more stable. And is also that steady state was reached, no more bands were forming. And the band spacing from simulation was 2.8 times the radius, and the experiment was 2.4 R, right? So it clearly says that the migration, okay, and secondary flow, they are enough to basically explain the pattern formation, right? There were no bands when we used diffusive flux model, because diffusive flux model does not predict secondary current. And there were no bands even with SBM when we took an isotropic tensor. So this tells us that it's the rheology which is more important, okay, compared to instability in explaining the band formation. So this is the final band from simulation and from the experiment. We also, if you consider the weaker bands, they also observed 11 bands. We also observed 11 bands. Right? So I don't have time, so how much time I have?
2 minutes 15 seconds.
2 minutes 15, okay. Yeah, I can use that time to explain that how we can control suspension transport in rotating annular flow. So there was accident, which was also mentioned in one of the speaker, Gulf of Mexico. It happened in one of the oil wells of BP. And this occurred because there was failure of production casing, and which resulted because of poor cementation. So in oil well, you have, to stabilize the hole which was drilled, you put a pipe and you put cement in the annular spaces. So if cement is not good, it's going to fail. And this cement, cement slurry has particle, in fluid. So if there is a migration, it's going to result to poor cementation. So this problem, we got basically idea from Bird Stewart Lightfoot. They have, in the TP textbook. For Newtonian fluid, you can see this problem. We did, instead of these inner cylinder, we started rotating it. And what we saw at different RPM, I'll just go to final slide. Okay, these are various RPM, and these are the particle concentration contour. Yeah. What we observed is that as you increase the rotation rate of the inner cylinder, the migration is suppressed, right? So it becomes more and more flatter. Right? This was the axial profile. So this just shows that we have done simulation where steady state was reached and enough length of the cylinder was there. Okay? So this gives us a fair good idea that if while pumping the cement slurry, if you rotate the inner cylinder, you can control the migration, and in a way you can go for better cementing operation. So with that, I would like to summarize that if in a mixture of bi-density, the heavier particle, they try to disperse the lighter one, so they act as a micro mixture for the dispersion. And for the migration suspension balance model, okay, effectively has predicted the axial and radial segregation patterns, and the wavelength patterns matched with the experiment, right? And that's all. So I would also like to thank Jong-Hoon Lee, who helped us in carrying it out point particle simulation. And I also like to thank John Brady. Actually, this rotating suspension, we had discussed a lot when I was visiting Caltech. Though the whole discussion was about finite size particle, I'm still looking at how to simulate finite size particle. And my students also benefited by interacting with Professor Knott, when they were doing summer training, and they passed on knowledge to the graduate student. So with that, I would like to end, and I thank you all for attention.
Okay, we have time for a few questions.
Yeah.
No.
Thank you. You showed an enormous amount of data.
Yeah.
And so you have varying particle densities, particle sizes, particle shapes.
Yeah.
But there are two other particle properties in the problem.
Okay.
And I wondered if they were important in what you showed us or not for the segregation, and that's the friction or the coefficient of restitution of the particles with themselves, with the other particle, and with the walls.
Yeah.
And so I wondered, in these, are they having all similar angles of repose, or do you have a sense of what the interaction is at the surface of the particles?
You're talking about experiment, because simulations were all, the sizes were same. They were spherical.
No, I meant in the experiments.
In the experiment,
right?
yeah.
You have many different properties you're trying
Yeah.
to make these maps for. And I was just wondering, do we need to worry about the roughness or the...
We have not considered, because these particles were fairly smooth. So some of the particles which we use were nylon particle, but for other cases when I had spherical settling and spherical floating, they were all polystyrene particles, spherical in shape. So I'm not sure about cylindrical particle. Yeah, I agree that they will have different sort of.
Were the walls?
The walls were always smooth. They were the cylinder was made from the glass cylinder.
Okay.
Yeah, they were perfectly smooth, and anyway the fluid was there, so there was no friction between particles and the wall. Yeah.
Any other questions? So can I ask you a question, Anugrah?
Yeah.
So the model that you said you used with an anisotropic normal stress tensor, that is not frame invariant.
Yes, that's a good question. So it's a 3D flow. You do not have for suspension balance for 3D frame invariant. Still, I don't find there is frame invariant by a group by Morris. They have extended it for in 2D case arbitrary geometry, right? But this is the case where you have 2D symmetry, right? It's an axis symmetry case, right? So we still use frame invariant model. Okay? It works only in this case. If I go to complicated geometry when you don't have circular cylinder, we can't use it. But we were fortunate that this is an axis symmetry case. So we can still use frame invariant suspension balance model, frame variant suspension model.
And the simulations were again with point particles like LAD? LADs
In fact, we used their code.
Okay.
Yeah.
Are there any other questions? So if not, let's thank Anugrah again.
Yeah. Thank you.